Okay, hey guys. Today we're going to be doing some maths, some FP2 from the exam that was sat in June 2014, and we're going to be looking at question 7. Quite an interesting question, so two parts to it. The first part can be done. Get the question in front of you, otherwise this ain't going to make any sense, alright? Make sure you've got the question in front of you when I'm talking about this. The first part can be done in two different ways. We can either use a formula booklet or we can derive it from first principles. That's the way I'm mainly going to be showing you how to do it today, because the exam will ask you to derive things from first principles. It will ask you to differentiate inverse trigonometric functions from first principles. So we need to know how to do it. I'll show you the other method briefly though. The second part of this question, I've just looked at it now, I looked at this about 10 minutes ago. Second part of this question, when I first looked at it, I was like, what's going on? I can't see any way to do this. And then I actually put pen to paper, and about 30 seconds later I got myself 3 marks. So, you know, it was alright. Quite an interesting one. Let's get on with it. Question 7a. So, we've got y is equal to inverse tan of 1 plus x over 1 minus x. And we want to be able to differentiate that. How are we going to differentiate that? Like I said, two different methods. Either from first principles, which is going to be the method I'm mainly talking about, but you can also use a formula booklet. In the formula booklet, they tell you if y is equal to tan minus 1 of x, then dy by dx is equal to 1 over, is that a minus or a plus? It's a plus. 1 plus x squared. Now we can use this rule from the formula booklet together with the chain rule, which you should be familiar with from normal maths A level, from C3. We can use this together with the chain rule to differentiate this really quickly. Remember how the chain rule works. Dy by dx is equal, once you've made a substitution, is equal to dy by du multiplied by du by dx. So if we call this whole thing u, then dy by du is 1 over 1 plus u squared, and du by dx is the derivative of just a fraction here with respect to x, and you can do that using the quotient rule. Multiply them together, you got your answer. Not too bad. We're going to do it though from first principles, because like I said, you might have to prove this result for yourself in the exam. So you need to know how to do it. It doesn't take too much longer, so why not? Why not just go ahead and do it? Alright, okay. How do we differentiate this? We don't know how to differentiate an inverse trigonometric function. We know how to differentiate a normal trigonometric function, so let's get back to that. Let's apply tan to both sides to get rid of the inverse trigonometric function. So this gives us tan y is equal to 1 plus x over 1 minus x. Now I can differentiate both sides implicitly with respect to x. So the left-hand side, the derivative of that, well, the derivative of tan is sec squared. But remember, because I'm implicitly differentiating, I need to remember the derivative of y with respect to x. So my left side is sec squared y dy by dx. And on the right side, I differentiate this using the quotient rule. vu dash minus uv dash over v squared. I'm going to do it all in one go. I think you should be able to do this all in one go yourself. So v is 1 minus x. U dash, in this case, would just be 1. Minus, how does it go? vu dash minus uv dash, so 1 plus x. Times by the derivative of, so v dash, the derivative of v. The derivative of this would be minus 1, so we just make that minus into a plus. And then all over v squared, which is 1 minus x squared. And now I'm going to say what dy by dx is. So I'm going to make dy by dx a subject. Well, the top part here of our fraction, that simplifies quite nicely. 1 plus 1 is 2, minus x plus x just cancels. So that gives me 2 over 1 minus x squared, 1 minus x all squared, and then I'm going to divide by this x squared y. Cool, okay. Now, we don't know what sec squared y is. We want dy by dx. We've still got a y in it, which is a 9. We want everything in terms of x. We don't know what sec squared y is. Hang on now. We know what tan y is, and there's something that links sec and tan, remembering our trigonometric identities. Now, the only trigonometric identity I ever remember, because I hate memorizing things, I was about to say memorizing. The only one I remember is cos squared x plus sine squared x equals 1. How can we get that to something with a tan squared in and a sec squared in? Well, to get tan, I do sine divided by cos. So I'm going to divide both sides by cos squared. Cos squared divided by cos squared is 1. And then I've got my tan squared y, and that equals sec squared y. I've gone from x's to y's, but you know what's going on. So sec squared y is 1 plus tan squared y. So this gives us 2 over 1 minus x squared times 1 plus tan squared y. Cool. And now tan squared y we can write in terms of x now. Hooray. Tan y is 1 plus x over 1 minus x. So tan squared y, you just square that. You just square that. So dy by dx. Oh, I think I might be going off the bottom of the screen here. No, we're alright. We're alright if I stay to about here. Okay. dy by dx then is 2 over 1 minus x squared times 1 plus tan squared y. So this squared. 1 plus x. And I'm going to square the top and the bottom individually. I was going to do it all in one big bracket, but I think it'd be easier for you to see if I do it in 2 separate brackets. Cool. No, I haven't gone off the screen. Perfect. Okay, so now what we've got to do is just a little bit of rearranging, to get this whole thing to what the answer says. You know, we're given the answer in this question. So we've got to get this to the answer. Okay. Well, the first thing, hopefully you can see there, is we've got this 1 minus x squared, and we've got a 1 minus x squared here. So those are going to be able to cancel out if we make this whole fraction a fraction over 1 minus x all squared. So this 1, I'm going to change to 1 minus x squared all squared over 1 minus x all squared. And that should allow me to cancel these out. So dy by dx is equal to 2, put it in the middle this time, over 1 minus x squared all squared. Now this 1 I'm going to make, like I said, into that fraction 1 minus x squared over 1 minus x squared plus 1 plus x squared over 1 minus x squared. Cool. And now what we're going to do is we can combine this fraction and the denominator, whatever this bottom bit is called, that will cancel out with this here. So we'll have this cancelling out with this, and that will give us 2 over 1 minus x all squared plus 1 plus x all squared. And if we simplify these, 1 squared is 1 plus 1 squared is 1, so that gives us 2. Twice the product is minus 2x here. Twice the product here is 2x. So minus 2x and 2x will cancel out. And I've got x squared plus x squared, so plus 2x squared. If I divide that whole fraction by 2, I get the answer, 1 over 1 plus x squared. So not too bad doing it from first principles. You can use a formula booklet. The mark scheme's happy with that. Get used to doing it this way though, because you may be asked to do it this way, so you need to know what to do. And I don't think that was too bad. I think that was all right. Okay, part B. Like I said, this one really freaked me out to begin with. I didn't know what was going on. Didn't know how I was going to get that answer. I don't think I've seen this type of question, or this, this type of logic used before. Maybe. Answers on a postcard. Right. Okay. So we've got this function, y, which equals tan, the inverse tan of 1 plus x over 1 minus x, plus the inverse, or minus, sorry, the inverse tan of x. And we're told in the question that for whatever value of x less than 1, x can't be equal to 1 here, because otherwise, the universe would implode when we divide it by 0. We're told that this equals pi on 4. And I was looking at that thinking, how am I going to get that? What's going on here? What am I going to do? I don't know. Am I going to let everyone down later? Well, no, I didn't. This was the function that we differentiated in the first part of the question. And the question starts with hence. So we're going to use the first part of the question, and we differentiated this in the first part of the question. Well, if we differentiated that in the first part of the question, and we know we're going to have to use the first part of the question, let's differentiate everything and see what happens. Because I know what this differentiates to. And I know what that differentiates to from my formula booklet. Okay. So dy by dx, this differentiated to 1 over 1 plus x squared. And then you look in your formula booklet and you see that that's also 1 plus x squared. So that's 0. And then I could see what was going on. Then I had it. Then I pretty much had my 3 marks. So what does that mean if the gradient of a function is 0? And it's not just like 0 at one point. We haven't said when x equals 10, the derivative is 0, so there must be a maximum or minimum point at 10. No. X could be anything. X could be whatever you wanted it to be. Well, less than 1. X can be whatever you want it to be, and the gradient is always 0. So what does that mean? If whatever you stick x in, the gradient is always 0. So wherever you are on your graph, the gradient is always 0. Well, what have you got? You've just got a flat graph. If everywhere along that graph the gradient is 0, that is a constant graph. That's a constant value. So what we can say is that y is equal to k for some constant k, or capital C, whatever. You might like that, I don't know. Whatever you want. So once we know this is a constant, all we've got to do is find out which constant it is. Probably pi on 4. But how can we find out which constant it is? Easy, just stick in any value of x whatsoever. Make it an easy one. Stick in x equals 0 into here, and you get pi over 4 as your answer out. And because this is a flat graph, the whole function must be equal to pi over 4. Weird question, right? I looked at it, I couldn't see what I was going to do, and then it all became clear when I saw the gradient was 0. And like I said, I knew to do that because of the hence. The word hence told me I'd probably have to differentiate. Alright, that's it for another episode of Andrew Does Maths. Hope you enjoyed it. Hope it helped. Let me know if you've got any questions, comments, whatever. You want me to go into more detail, you want me to do another question, a completely unrelated question. make it on FP2. I'm not talking about geography or whatever. But yeah, just let me know how I can help. Cool. Okay. Good luck.